Hello everyone, welcome back to A4 Analysis. This is the fourth episode of Study Statistics with me. Today I was going through discrete distribution and here are a few of the highlights of what I studied. First of all, when it comes to discrete distribution, we would like to know about random variable because this is one of those terms which has been used really frequently throughout this chapter. So random variable is a variable which contains outcomes of a chance experiment. Now, random variable can be of two types. One is discrete random variable and the other one is continuous random variable. If the set of all possible values of a random variable is at most a finite or countably infinite number of possible values, then we will call it a discrete random variable. So in easier words, I would say discrete random variable is the random variable which takes discrete values, or of course it will take some finite number of values. On the contrary, the continuous random variable takes on every possible value, every point over a given interval. So the values are not discrete, the values are rather continuous. That's the difference, and it can take every point over a given interval. Next is discrete and continuous distribution. So the outcomes for discrete and continuous random variables and their associated probabilities can be organized into distributions and they will be called as discrete and continuous distributions respectively. Now let's talk about few more things here. First one is expected value or mean. Expected value or mean of a distribution is the long run average of occurrences. So expected value is denoted by the sign mu and it is equal to the E of x. This is also expected value of x, or we sometimes call it mu, is equal to summation of x into probability of x. So it will be like x1 probability of x1 plus x2 into probability of x2 plus x3 into probability of x3 and so on. So E of x is the expected value of x is the outcome, and P of x is the probability of the outcome being x. Variance, which is sigma square, I'm not sure how it came up as the square is coming up here. I will correct this, but this should be as sigma square equal to summation of x minus mu square into probability of x. Similarly, standard deviation will be sigma, which is equal to square root of variance. So it is root over summation of x minus mu square into probability of x, or P of x. Next, we will talk about a couple of discrete distributions. The first one in the list is binomial distribution. So there are few characteristics of binomial random distribution. First of all, of course, this is a discrete distribution. Then there should be a fixed number of identical trials in the experiment. Number two, the outcome of each trial can be classified in two possible outcomes, which is success and failure. Number three, trials are independent of each other. And number four, the probability of success in each trial remains constant. So if any random distribution follows all of these characteristics or possesses all of these characteristics, we would call it a binomial random distribution. Now let's look at the expected value of binomial random distribution. Here the expected value or long run average is equal to n into p, where n is the number of trials and p is the probability of success. Then we have variance, which is sometimes written as var of x. It will be equal to n into p into 1 minus p, where n is the number of trials, p is the probability of success, and 1 minus p is the probability of failure. Similarly, standard deviation is of course the square root of variance, and as you can see it is root over n into p into 1 minus p. This is about binomial distribution. Moving on to the next distribution is Poisson distribution. Now this is the word I struggle a little bit to pronounce, but I'll try my best. So Poisson distribution is another discrete distribution which is similar to binomial, but it's not fully similar, of course, otherwise why would we have a similar distribution with a different name. Poisson distribution, so for binomial distribution, it describes a distribution of two possible outcomes, whether it can be success or failure from a given number of trials. But on the other hand, Poisson distribution focuses only on the number of discrete occurrences over some interval or continuum. Also, it does not have any given number of trials. So one example which really stood out to me while I was going through this chapter was Poisson distribution. An example of Poisson distribution can be within 30 minutes, in an interval of 30 minutes, the number of old cars that went through a gas station. That can be a Poisson distribution. So we are talking about the number of discrete occurrences. Also, we are giving a interval. So this can be an example of Poisson distribution. Characteristics of Poisson distribution. So the first one is, of course, this is a discrete distribution. This complete chapter was about discrete distribution. So Poisson distribution is also a discrete distribution. Poisson distribution describes about rare events. Number two, each occurrence is independent of other occurrence. So this is also looking similar to binomial distribution. The occurrences in each interval can range from 0 to infinity. So we don't really know the number of occurrences. It can vary from 0 to as high as infinity. Number 4, the expected number of occurrences must hold constant. The expected number of occurrences, this is expected value or mean of occurrences, must hold constant throughout the experiment. Now this looks something special about Poisson distribution. Let's talk about the long run average of Poisson distribution. It's called as lambda, and probability of x in case of Poisson distribution can be expressed in terms of lambda, and it will look something like this, which is lambda to the power x into e to the power minus lambda over x factorial. So here probability of x is equal to lambda to the power x into e to the power minus lambda by x factorial, where x is the number of occurrences per interval for which the probability is being computed, lambda is the long run average, and e is the base of natural logarithm, which is also 2.718 approximately. Mean or expected value of Poisson distribution is lambda, variance of Poisson distribution is also lambda, and standard deviation is root over lambda. Approximating binomial problems by Poisson distribution, that is possible, and I have just given some links here. You guys can check it out, find some examples, find the formulas, but for the time's sake, I'll move on to the next and the last distribution what I studied today, that is the hypergeometric distribution. So hypergeometric distribution is actually used when the samples are taken without replacement. So binomial distribution applies in theory only to the experiments in which the trials are done with replacement and the events are independent. But hypergeometric distribution applies only to experiments in which the trials are done without replacement. Now the characteristics of hypergeometric distributions are as, first one, each trial has only two possible outcomes, success or failure. So it looks like a binomial distribution so far. Number 2, sampling is done without replacement. Now this is where it is varying from binomial distribution, because in binomial distribution the sampling is done with replacement. Number 3, population size capital N is finite and known. And number 4, the number of successes in the population capital A is known. And here probability of X for hypergeometric distribution will be equal to ACX into n minus AC n minus x by NCN. Now this is actually, okay, I will, even though I read it out, it probably doesn't make any sense when somebody is hearing it. So I will explain it a little bit further. So capital N is the population size, small n is the sample size, capital A is the number of successes in the population, and small x is the number of successes in the sample when sampling is done without replacement. So in the numerator we have how many ways we can select x out of A. So A is the number of successes in the population. Out of the number of successes, out of all the successes in the population, how many combinations of X is possible into out of the rest of the samples, means N minus A, capital N minus capital A means total population size minus the total number of success. So we are taking just the number of failures. How many ways we can, how many combinations of N minus X is possible. So N minus X is in sample. Okay, so I have to repeat this again probably. First of all, if A is the number of total number of successes in the population and small x is the total number of successes in the sample. So in the numerator the first term is out of the total number of successes how many ways I can select x, and then out of the total number of false in the entire population how many ways I can take n minus x. N minus x is also the number of failures in the sample. Now this is divided by NCN. So how many ways I can select a sample of size small n from a population of size capital N. So this is a combination. These all are three combinations and this is the formula. So the denominator is actually how many ways, the total number of ways we can get the sample of size small n from a population size of capital N, and these two are only giving me the combinations in how we can select the success outcomes. Because of the multiple possible combinations of the three parameters capital A, capital N and small n, using hypergeometric distribution can be tedious and time consuming. As a rule of thumb, if the sample size small n is lesser than 5% of the population, we can still use binomial distribution instead of hypergeometric distribution when sampling is done without replacement. Now, this is possible only because when the population size is too high or when the sample size is less than 5% of the population, in that case, sampling without replacement does not create much of an impact. That is the reason we can accept binomial distribution in such cases. So yeah, I think that's it for today, and we will meet again very soon. I know this series has been a little bit on the boring side, but we'll see how we can progress and how we can make it better in future. So till that, keep learning, keep sharing these videos with your friends and whoever is interested in data science, and let me know in the comments what videos you would like to see in future. Bye guys.